Now that we've studied the terrestrial planets, let's take a look at the Jovian planets. We're going to try to stick to our comparative planetology approach as we examine them. First of all, I just wanted to show you something that I think is kind of interesting for a number of reasons. You might wonder, how long would it take us to get from a spaceship to get from the Earth to Jupiter if we wanted to look at it? And the spacecraft that has really taught us the most about the Jovian planets is Galileo, which was launched in the late 80s. And here is actually the path that Galileo took as it went from the Earth to Jupiter. And you might actually wonder, why did it take such a roundabout way? And that's kind of interesting, and it has something to do with gravity that we learned about earlier. Because you'll notice that along this path, the Galileo spacecraft actually passed close by different planets like Venus and Earth, and even a large asteroid as it got to its path to Jupiter to observe. And the reason it was doing that is to save fuel. It would actually use the gravitational field of these objects to accelerate it, and it used what we call the gravitational slingshot, which is why it's not really a straight shot, but it kind of swings around and gets accelerated, and then it can continue on till the next slingshot. So I thought that was kind of interesting, and as you can see, it took a little bit more than 6 years for it to get to Jupiter. So let's take a look at the Jovian planets all next to each other. And you'll see that they almost seem to subdivide them into two groups. Jupiter and Saturn look very similar in their size and their appearance, except for the very big ring system that Saturn has. And then when you look at Uranus and Neptune, they're similar in size and similar in appearance. And so as we go through and look at the Jovian planets, we're going to sort of look at how Jupiter and Saturn look like on the inside and how they're similar, and the same thing we'll do with Uranus and Neptune. So first of all, let's talk about what the Jovian planets are made of. For Jupiter and Saturn, they're mostly hydrogen and helium gas. Again, remember that the Jovian planets are large gas planets, and the reason that the gases were available to make the planets was because they formed out beyond the frost line. So there was much more material available to come together and to form the planets. Hydrogen and helium was not available to form in the region where the terrestrial planets formed, which is why that they're much smaller and basically just rocky. Uranus and Neptune are mostly have compositions of hydrogen compounds, water and methane and ammonia. They do have some hydrogen, helium, and rock. That would be at the very center. So let's look at a cutaway view, and interestingly, we still have sort of this differentiation where we have different layers of material, and notice that the very core of all our Jovian planets is some sort of rocky and metal core. So those materials were still available to sort of almost like the seeds of which all the other material was going to form around. And it's just that the hydrogen and helium compounds were available to coalesce around those rocky cores. Saturn and Jupiter have something in common. They have a layer of what we call metallic hydrogen. And keep in mind that these planets are huge, and so the conditions within them are kind of unusual. And so hydrogen on Earth is not a metal, but we call it metallic hydrogen because basically it acts like a metal when it's under the high pressures that it is in the interior of Jupiter and Saturn. And when we say it acts like a metal, the main thing that we're talking about is that it conducts electricity, so there's free ions in that hydrogen. Then we get a layer of liquid hydrogen above that, and then the gas layer. So what's really kind of weird about the Jovian planets, and we can think about it right now for Jupiter and Saturn, is even though they have this layer of gas, in a way there's like no solid layer is like no solid surface that you could stand on for these planets. They are these gas giants, which is kind of crazy when you think about it. And it's not, even though there's sort of a gas layer and a liquid layer, it's a gradual transition. So it would be, if you were going down into the clouds, it isn't like you would all of a sudden hit this sea of liquid hydrogen, but you would sort of be going into something that was like increasingly misty, and have the droplets of water, and it would just be this gradual transition into, suddenly you would find yourself immersed in a totally liquid environment. So it's just something that's really unlike anything that we experience here on the terrestrial planets. When we look at Uranus and Neptune, we notice that they're similar to each other in their interiors. They have, again, the core of rock and metals, but then the next layer that they have is sort of water, methane, and ammonia. So they don't have the metallic hydrogen because of their much smaller size. The conditions inside of the planets is not extreme enough to have hydrogen act like that metallic material, so it's just different. And then they have a layer of gas hydrogen and then the clouds. So we already talked about the fact that the Jovian planets don't have a solid surface, and we also mentioned that the layers are under very high pressures and temperatures, and that's basically because of the incredible mass and size of these planets. The cores are, relatively large, but if you compare them to, Earth in terms of their mass, but they are very, very compressed because of the large amount of material sitting on top of them. So I already talked about the fact that we do have this layer of metallic hydrogen inside of Jupiter, and remember that that is why we call it that, because of the fact that it acts like an electrical conductor. So again, here's just another summary of the different interiors. We've already really compared and contrasted them, but you start to see why we like to group the Jovian planets into Jupiter and Saturn have a lot in common and are very similar, and Uranus and Neptune have a lot in common and are very similar. You might be familiar with Jupiter's colors. When we're looking at the bands of colors on Jupiter, we're actually sort of seeing what is like the weather patterns on the planet, and there are bands because the winds are going across the latitudes, like around the planet, and there's also areas where high pressure and low pressure, so a light band will be lower or higher than the adjacent dark band, and there's sort of some circulation going on between them. The colors come from different materials that are within the clouds, some ammonia, ammonium sulfate, and other compounds give them their colors. And notice that it's also how large everything is. Saturn is a little bit more subtle, but it still sort of has that banded structure that we see on Jupiter, and the colors are a little bit more subdued. The reason that Uranus and Neptune have the blue color is because of the high amount of methane that they have within their clouds, and what it does is it absorbs the red light and transmits the blue light, and then that's why the planets look blue, because of that methane and what it does to the sun's rays. You're probably very familiar with Jupiter's Great Red Spot. This has been observed for over 300 years, and we believe that it's something like, sort of like a hurricane. It's a region of where there's high pressure, and you can see a lot of rotation in the movement of the clouds. But unlike hurricanes here on Earth, it has this incredible staying power, which is probably due to the fact that there's no solid surface underneath it to sort of break it up when it hits it. So it can really just be sustained for a very long period of time. So when we talked about the terrestrial planets, we were interested in whether or not the Jovian planets, we were interested in whether or not a planet had a magnetic field. And just to remind you, remember the things that we needed to have a magnetic field is we needed some sort of electrical conductor inside of in the interior of the planet, and we needed that to be moving. So for a planet like Earth, the outer core of the Earth is liquid, and it's made up of iron and nickel, which are metals, and so that was the electrically conducting material. So at first the expectation was that the Jovian planets wouldn't have magnetic fields because they don't have sort of that similar metal interior, but they actually found that Jupiter and Saturn, well, all the planets do have very strong magnetic fields. So it was a time for scientists to sort of try to figure out, well, what causes this? What is the source of the electrically conducting material? And we sort of spoiled the surprise. It is due to the layer of liquid metallic hydrogen inside of both Jupiter and Saturn. Because the hydrogen acts like a conducting material, because there's free electrons that can move around, this actually allows it to generate magnetic field. And even though Jupiter and Saturn are extremely large, their rotation rates are very fast, which helps them again generate extremely large magnetic fields. Saturn, same thing, has a magnetic field, but what's interesting is Uranus and Neptune have magnetic fields. The white axis here is actually the rotation axis, while the red axis is the magnetic axis. And you see that those aren't very well aligned for Uranus and Neptune. And of course, the question is, well, how do Uranus and Neptune create their magnetic fields? Because they don't have the liquid metallic hydrogen. And we believe that it's because of the methane and ammonia dissolved in that water layer is because those are dissolved and then there's ions floating around, that might be how they create their magnetic field. And so we're not going to be talking about the moon, so we'll just stop here and then we'll continue on and talk about the ring systems for the Jovian planets.